Let's examine another kind of sorting algorithm. The merge sort consists of 3 steps. First, we divide the stack into 2 halves. 2. Sort each half. And 3. Merge the sorted halves back together. Let's look at an example. Consider the stack 3, 1, 7, 6, 2, 8, 9, 4. Let's sort this stack in ascending order. First, we divide the stack into 2. Since there are 8 elements, we dump the top 4 elements to the new stack. Now there are 2 stacks, 2, 8, 9, 4, which was the bottom half of the stack, and a new stack, 6, 7, 1, 3. Next, we sort each of the 2 smaller stacks. First, let's sort 2, 8, 9, 4. As before, we split this stack into 2, the stack 9, 4 and the stack 8, 2. Again, we sort the 2 child stacks first. Let's begin with 9, 4. As before, we split the stack into 2, stack 4 and stack 9. Then we sort the 2 child stacks. The result of sorting a single element stack is simply itself. In other words, the result of sorting stack 4 is just stack 4, and the result of sorting stack 9 is stack 9. Now that we have 2 sorted halves, we can merge them. The merge process is straightforward. Suppose that we have 2 stacks A and B, and an empty merge stack M. Here's the algorithm. If the top element of A is less than or equal to the top element of B, pop A and push the element to M. If the top element of A is greater than the top element of B, pop B and push the element to M. Repeat steps 1 and 2 until one of the stacks are empty. Then dump the rest of the other stack to M. Finally, reverse M. Let's use this process to merge the stack 4 and stack 9. Here's a tabular view. Initially, stack A is 4 and stack B is 9, and the result is empty. Since 4 is less than 9, we're going to pop 4 and push it to M. Now stack A is empty. Since stack A is empty, we're going to dump stack B to M. And the result is the stack 9, 4. Since we push the smallest elements first, M is sorted in descending order. We then reverse M so that it is sorted in ascending order. Then the result of merging stack 4 and stack 9 is equal to the stack 4, 9. Now that stack 9, 4 has been sorted, we sort the second half, which is the stack 8, 2. We use the same process to split stack 8, 2 into stack 2 and stack 8 and merge them. The result of merging stack 2 and stack 8 is equal to stack 2, 8. Now that the child stacks have been sorted, we can merge them. Here is a tabular view of the merge process. Stack 1 is 4, 9, and stack 2 is 2, 8, and M is once again empty. First we compare 4 and 2. Since 2 is less than 4, we're going to pop 2 and push it to M. Then we compare 4 and 8. Since 4 is less than 8, we're going to pop 4 and push it to M. Now we compare 9 and 8. Since 9 is greater than 8, we're going to pop 8 and push it to M. Finally, stack 2 is empty, so we're going to dump stack 1 to M. And the result is the stack 9, 8, 4, 2. Once again, we reverse this result to sort in ascending order. and the result of merging stacks 4, 9, and 2, 8 is the stack 2, 4, 8, 9. Here's an animation that sorts the stack 2, 8, 9, 4. Now that the first half of the stack is sorted, we sort the other half, which is the stack 6, 7, 1, 3. We follow the same process. We split this into the following two stacks, 1, 3, and 7, 6. Then we split 1, 3 into stacks 3 and 1. We then sort and merge the two single element stacks. The result of merging stacks 3 and 1 is the stack 1, 3. Similarly, the result of merge sorting stack 7, 6 is the stack 6, 7. Now we merge stack 1, 3 and stack 6, 7. Here's the procedure. Stack 1 is 1, 3, and stack 2 is 6, 7, and M is once again empty. Since 1 is less than 6, we're going to pop 1. Then we're going to compare 3 and 6. 3 is less than 6, so we're going to pop 3. Now stack 1 is empty, so we're going to dump stack 2 into M. First 6 is popped, and then 7 is popped. Then we reverse the result. And the result of merging stacks 1, 3 and stack 6, 7 is the reverse of stack 7, 6, 3, 1, which is 1, 3, 6, 7. Now that both halves have been sorted, we can merge them to get the final result. Once again, here's a tabular view of the merging process. Stack A is 2, 4, 8, 9. Stack B is 1, 3, 6, 7, and M is initially empty. 2 is greater than 1, so we're going to pop 1. 2 is less than 3, so we're going to pop 2 next. And then we compare 4 and 3. Since 4 is greater than 3, we're going to pop 3. Then 4 is less than 6, so we're going to pop 4. 8 is greater than 6, so we're going to pop 6. Next we compare 8 and 7, and since 8 is greater than 7, we're going to pop 7. At this point, stack B is empty, and so we're going to dump the rest of stack A into stack M, and the result is the stack 9, 8, 7, 6, 4, 3, 2, 1. Once again, we reverse the result to sort in ascending order. Then the result of merging stacks 2, 4, 8, 9 and 1, 3, 6, 7 is the stack 1, 2, 3, 4, 6, 7, 8, 9. Finally, after using the transitive property a few times, we can conclude that the result of merge sorting stack 3, 1, 7, 6, 2, 8, 9, 4 is the stack 1, 2, 3, 4, 6, 7, 8, 9. In general, if the result of having the stack S is equal to the stack first half and second half, and MA is equal to the result of merge sorting first half, and MB is equal to the result of merge sorting second half, then the result of merge sorting S is equal to the result of merging stacks MA and MB. For example, since the result of having stack 6, 7, 1, 3 is equal to the stack with the first element 1, 3 and second element 7, 6, and the result of merge sorting 1, 3 is equal to 1, 3, and the result of merge sorting 7, 6 is equal to the stack 6, 7, we conclude that the result of merge sorting stack 6, 7, 1, 3 is equal to the result of merging stacks 1, 3, and 6, 7. The result of merge sorting stack A equals stack A. For example, the result of merge sorting stack 3 is equal to stack 3. Here are the properties that describe the merge process. Result of merging stacks A and B is equal to the output of the merge stacks function, where input stacks are A and B, and the merge stack is empty. If A is less than or equal to B, then the top element of stack A is popped and pushed into the merge stack. If A is greater than B, then the top element of the stack B is popped and pushed into the merge stack. If stack A is empty, then we start popping from B and pushing it to the merge stack. If stack B is empty, then we dump stack A into the merge stack. Finally, if both stacks are empty, then the output of this function is the reverse of the merge stack. And here are the properties that describe the halving process. Result of halving the stack S is equal to the output of the half stack function, where input stack is S, the other stack is empty, and the count is the length of stack S divided by 2. If C is greater than 0, then we pop from the original stack and push it to the other stack. On the other hand, if count is 0, then the result is a 2-element stack, where the first element is what's left of the original stack, and the second element is the other stack.